It's Dugan Ashley. Hey, how's it going? Dugan the Zogbane Ashley here. Oh boy, if you stand on a Rothschild flag for 2 seconds, you are going to get so many boomer rage comments. It's very offensive. You
silly
Zog boomers, when you're on there typing away with your fingers, they're talking to me about being sympathetic to jihadis and not being patriotic. Bro, I've fought jihadis in the Middle East. What have you done? If you didn't deploy in the GWOT, if you haven't snatched people out of their beds during raids and been shot at by enemy, if you've never seen your opposition that you're fighting dissolve overnight practically, and all that it took was a couple of briefcases of cash getting passed out, if you've never seen a bunch of KIA and WIA and then all of everyone's hard work goes away like that and they hand it over and say, good job, pat you on the back and send you home, if you've never seen that, then you have no realistic conception or idea how warfare works, especially modern warfare. And you're going to complain and whine about how I don't support sending Generation Z to become Persian fertilizer. If you've been there, I care. I'll listen to what you have to say. You've got the right. But these Zog boomers, like, this stuff is outrageous. You flipping people have no call to come in here and talk to me. You're traitors. If I had my way, which you're lucky that I don't, because you'd be facing a wall. There is no such thing as dual loyalty. You're either loyal to the United States or you're loyal to Israel. There's no in between. You are not going to convince me to send 18-year-old kids once again to the Middle East to fight Israel's enemies for them. If you want to support the Israeli project, the Greater Israel Project, where they're expanding, later on they're going to have to take portions of Egypt and Jordan and Syria, and it's just going to keep on going. If you want to be a part of that, then you should enlist and go fight. And then when you do it, you should stay there and not come back. Zog boomers. They're worse than British sympathizers in the Revolutionary War, I'm sure. Much more annoying, at least.
Energetic America.
Explosives aren't hard to make, guys.
Accelerate.
Okay, this is Advanced Explosive Design Part 2. This is Pyrovalence, a dedicated video. That means that this is going to be academic, so if you don't want to do any math, this probably isn't the video for you. If you want to know how to make balanced explosive compositions that give you maximum energy out of the composition, or pyrotechnics for that matter, but we're going to discuss how to calculate proportions. There is a Part 1 in the library, Advanced Explosive Design 1. That video goes into specifics about what's going on with electron exchange. It's going to explain all of that in depth. I'm not going to do that in this video. We're just going to be moving past that to the next steps of how to efficiently use this stuff, especially in the field. There's going to be a field focus here. The best examples of pyrovalence are going to be in John Conkling's Chemistry of Pyrotechnics. I would recommend that book to anybody starting out in explosives or pyrotechnics. The latest editions are best if you can find them. They are floating around. They're PDFs floating around online, so you can find them. But the book is excellent. It's really going to give you a solid overview of the topic. One of the things I'm going to do is throw up on the screen here. These are charts from the book, and it's just kind of handy to have them in the video because when you're dealing with this topic, you can reference those. Here's a table for common elements that are used in pyrotechnics and explosives. Then we've got some tables that are going to be common fuels and oxidizers. Okay, so you can pause the video, reference those charts. They're really handy. Let's just get straight into it. The first most common operation that you would want to do when using pyrovalence is just simply balance some kind of fuel and some kind of oxidizer. What is a fuel and what is an oxidizer? There's a whole lot of fuels. There's quite a few less oxidizers. There are things that can have oxygen in them that are also fuels. Your common oxidizers would be things like nitrates and perchlorates and chlorates and nitrites, things like that. Those would typically be oxidizers. Metal oxides are going to be oxidizers. But right away, let's just do a simple calculation. Let's balance a composition of potassium perchlorate and titanium. So the first thing that you will do is write out whatever your identifier is so you don't get mixed up. KClO4. That's going to be my potassium perchlorate. And then I'm going to have titanium. The symbol for that is Ti. So every single time that you do this, it's always the same. You want two critical pieces of information about this molecule and this metal element. The first piece of information that you're going to want is the molecular weight for KClO4, potassium perchlorate, 138 0.5 grams is going to be 1 mole of the material. So that's the molecular weight, the molar weight, 138.5 grams. Titanium molecular weight is going to be 47.9. So the next thing after that you have to know is the pyrovalence value of both of these materials. So for potassium perchlorate, this is -8. Titanium is going to be +4. Anytime that you have a plus, it's always going to be a fuel. That's what identifies it as a fuel in the pyrovalence system. If you have a negative number, that is going to be an oxidizer. So potassium perchlorate was -8, titanium is +4. If you're not tracking how to get those numbers, you can watch the first video, Advanced Explosive Design 1. But the way that -8 comes from KClO4 is based off of the constituents in there, potassium, chlorine, and oxygen. And the number of them all together gives a pyrovalence total of -8. Titanium is just a single element, so it's +4 all the time, because if titanium got burned and it became oxidized, it would become titanium dioxide. That would have O2 on the end. O in pyrovalence is -2. So -2 times 2, that would be -4, right? Titanium's +4. You have to have a balanced metal to the oxide, so +4 to -4. So titanium is +4. So for balancing a composition for maximum energy output, this is all the information that you need. Those two pieces of information for each element. So the actual identity of these two materials is really, in sense of the pyrovalence calculation, we're replacing the name potassium perchlorate, we're just replacing that with 138.5 grams. 138.5 grams, that's potassium perchlorate. 47.9 grams, that's titanium. So the next step is to write that out. We're going to have 138.5 plus 47.9, and now we're going to do multiplication. We're multiplying the pyrovalence number, but we want to reverse them. We're going to switch them. So the +4 for titanium is going to go over here in front of KClO's number, which is 138.5. Now the sign of the number for this, for the purposes of pyrovalence calculations, you just discard it. So we have -8 is the pyrovalence for KClO4. We're just going to put 8 in front of 47.9. 47.9 is the titanium, right? By switching these around, we automatically set up a balancing in the end state. After the reaction takes place, this is going to be balanced and it's going to give maximum energy potential, theoretically. So the next step is to solve the multiplication. 4 times 138.5 equals 554. 47.9 times 8 equals 383.2. We now have a new number for each of these materials. So for potassium perchlorate column, we have 554 grams. For the titanium column, we got 383.2 grams. We're going to add those together and get a total of the composition in grams. Equals 937.2 grams. That is 100% of the composition, so we put over 100%. We don't know what the percentage is for each of these constituents that makes up this total, but we're going to find that now with cross multiplication of comparative fractions. Don't get wrapped around the axle on that, just listen to what I'm saying. We know the 937.2 grams is 100%, so we wrote 100% down there. We need to know what the percent is of 554. 554 is KClO4. So the way that we figure out what the percentage of that is to take that 100% down there, 100 times the 554, and then we're going to divide it by the numerator, which is 937.2 grams, which is the total, right? And it's going to give us 59.11%. That's our percentage of KClO4. Now for the calculator in the field, you just press -100. That's going to give you your remainder, which is going to be -40.88. We don't keep the sign, just disregard the minus, right? 40.88%. We already determined the potassium perchlorate. That means that this is going to apply to the titanium. So that's how you figure out how to balance the composition of a fuel and an oxidizer. Knowing this, you can pretty much make anything turn into an explosive. I mean, maybe it'll deflagrate, maybe it'll be low order. Some cases it'll go high order, but most things can be made into explosives. That mixture that we just did, titanium, potassium perchlorate, that's actually a really hot, I guess you would call it like an initiation mixture, pyrotechnic initiating mixture. It would be known as titanium potassium perchlorate, TPP. It's been replaced at large by titanium dihydride or titanium subhydride potassium perchlorate, which is known as THPP. It's a little bit slower and a little bit less sensitive and safer. But it's a really hot mix. It's pretty cool. It's a good example of a practical pyrotechnic a person would want to make. The next operation that somebody's going to want to do is going to be to analyze a mixture. So let's say you get a guy come up to you and he's like, hey man, I've got this pyrotechnic mix. It's KClO4, man. KClO4 at 80%, that's potassium perchlorate, is super hot. And then I got the titanium, is a 20%. 20% titanium. So 80% potassium perchlorate, 20% titanium. Comprende, vato? And then after that, you're like, why am I talking to this Mexican guy? Just kidding. Potassium perchlorate, 80%, titanium, 20%. That's your mix you want to analyze. So you write it out, KClO4, titanium, and now you're going to do a matrix column on the left. So you're just going to have categories of data that you're going to pull on this to analyze it. The first one that you're going to do is just what you already have, the information you've already got, weight of the comp, right? So W, that stands for weight. 80%, right, is what we said of potassium perchlorate, and 20% of titanium. Well, when you're doing an analysis, if you have a percent fraction like that, then you would just assume, for simplicity, that's 100 grams. So you would say 80 grams of potassium perchlorate, 20 grams of titanium. The next category that you're going to need is molecular weight. That's just like what we did before. Potassium perchlorate is 138.6 grams per mole, but we'll just put grams here. And titanium would be 47.9. So now for the analysis, you have to do an additional step. We got to take this data that we've already got, the column with the weight of the mix, and then the molecular weight, and we're going to figure out, okay, out of this molecular weight, how much of a mole do we actually have? Because that's what this is. This is a molar weight. 138.6 grams equals 1 mole. But we don't have 138.6 grams. We've got 80 grams. So what we do is we take 80 in the calculator, and we're going to divide it by 138.6. That's going to tell us how many moles of this material we're actually dealing with here. So for 80 grams, you've got 0.57 moles. And this category is moles, obviously, right? That's what you would label it as. For the titanium, we've got 20 grams, and we're going to divide it by the molar weight of 47.9. That's going to give us 0.41 moles. Then we take the piece of data that we also already have about potassium perchlorate and titanium, which is going to be their pyrovalence number. We already know that potassium perchlorate is -8 and titanium is +4. Now we have to do the last calculation, which is fractional valence. So to calculate your fractional valence, what's there, you're going to take the number of moles that you've got, 0.577 moles of the potassium perchlorate. We're going to multiply that by -8. It's going to give us an answer of -4.616. Then we go into the titanium. We're going to figure out what's the fractional valence here. 0.417 moles of titanium multiplied by a +4 valence. That's going to give us a total of +1.668. So we've got -4.616 for the potassium perchlorate and +1.668 for titanium. Now we just put these together. So we've only got two components here, and this is pretty straightforward. You've got a positive number and a negative number. Sometimes you'd have a bunch of components with like multiple oxidizers. The easiest way to do this is to add up your positives first and then just subtract all the negatives. So we'll do that. We've got the titanium last, which is a positive fuel, right? Positive 1.668. So we'll go 1.668, and we'll subtract the oxidizer, which in this case is potassium perchlorate, -4.616. And that gives the answer of -2.948. I don't need three figures on the end of this, so we're just going to round it up to 2.95. That means the sum of our fractional valences equals -2.95. Of course, you already know that a negative number, any negative number that you see in pyrovalence system, means that it's an oxidizer, right? So because this pyrovalence sum is negative, you know the entire composition is oxidizer rich, or fuel lean, depending on how you want to look at it, right? So this principle works no matter how many fields of data that you have, no matter how many materials in the composition. You're just going to have additional columns of materials. If you add more materials, if you added a binder here, if you added another oxidizer or another fuel, at the end, you're going to have some additional fractional valences that you'll just plug into that sum equation at the end to give you your final composition pyrovalence value. Now, what should a composition be? Well, that is the field of pyrotechnics or explosives that you're in, is to determine those things through testing. You need to determine, what is advantageous, why it's advantageous, but that can be something you can really wrap yourself around the axle with. And it's difficult to know what is desirable, for your particular needs. But this is a way that you can analyze it and understand what's going on and make logical decisions of where to start or to modify a composition. So if somebody came to me with this composition that we just did, and they say, hey, I've got this mix of potassium perchlorate, 80%, and titanium, 20%, I would analyze it and I would say, hey, this is, -2.95 on the pyrovalence. It's oxidizer rich. You could most likely get some more power out of this if you added in some fuel. If you added to this composition plus 2.95 of any fuel, it'll become a pyrovalent sum of 0 and be oxygen balanced. So how do we add 2.95 in the positive number a fuel? Well, we could add a different fuel, or we can take the fuel that's already there and we can boost it up. So let's OB this mix. We are short 2.948 pyrovalents for a fuel. So we got to add that. I'm going to use the titanium that we've already got because this fuel is already, we're already using in the comp. No need to bring in a different fuel. So I take the column of titanium. I'm going to look at the molecular weight. It's 47.9. So 47.9 grams is 1 mole of titanium, and that corresponds to plus 4 pyrovalents total. What I'm looking for is positive 2.948 pyrovalents number, but I don't know how many grams that is. To find that, what I'm going to do is take 2.948 multiplied by 47.9 divided by 4. That's going to give me 35.302. 35.302 is grams. This is the grams that you have to add to what's already there. You already had 20 grams. That's what we started with. We're adding 35.302. Now it's 55.302 grams total of titanium. At that point, you now have an oxygen balanced mix. You could go through and double check this if you want. It's oxygen balance. But there is one problem with it. You'll notice that you're no longer in a percentage weight proportion here. Because you're adding an additional weight of titanium, it's going to throw off the total, right? You're no longer at 100 grams. You're now over that. So let's figure out what the new total grams of this comp are. 80 grams of the potassium perchlorate plus 55.302 grams of the titanium. 135.302 grams is the total composition weight. That means it's 100%. Let's take the amount of titanium, 55.302, and let's figure out what percentage that is. To do that, we're going to multiply 55.302 times 100 divided by 135.302. The answer to that is 40.87. That is the percentage of titanium precisely. The next operation is to just subtract 100, 59.126, which is the percentage for potassium perchlorate. The mixture is now proportioned out into weight percentages, and you're oxygen balanced. You got it all set up. You can go back and you say, "Hey, Pato, I got a new comp for you. Super hot, it's OB. It's got so much oxygen available. It's got so much fuel available." I'm just
playing
around, having a good time. I gotta have a good time when I'm making these videos too. You know what I'm saying? And this stuff gets boring making you guys videos. And I'm gonna have to deal with your
darn
comments.